Hi children, welcome to the class. In this session, we are going to have a rapid revision discussion on chapter 1 of chemistry. As you can see in the board, unit 1, some basic concepts of chemistry. We are going to have a quick rapid revision. Even though it is quick and rapid, we are going to travel through the NCERT and we are going to review the important points in the NCERT and what all the main topics and points, concepts we need to concentrate on the chapter. Okay, welcome all once again to this rapid revision class. Chapter 1 Chemistry, some basic concepts of chemistry. If you go through NCERT, unlike the old editions of NCERT, we can find in the new edition there are few pages incorporated regarding developments of chemistry. I don't find anything from the exam point of view. There are not much of points in the area, but I would say it's an important area which will help you to understand the traditional ideas, particularly the ancient Indians, how much they had a great knowledge about the chemistry and the science behind in day-to-day life. It was well explained, and regarding our culture, regarding our traditions, how much we were having the informations and knowledge our ancient people had. It was well described in 2-3 pages, which you can see. So many important points. It is starting from the philosopher's stone, like that. You might have heard about all materials converted to gold, like that. Alchemist starts from chemistry knowledge, or the study of chemistry or thinking of chemistry starts from the alchemist contributions. That was the old contribution, alchemist, the people involved in such thinking. But mainly they were thinking of how the material can be converted to gold, like that. So ancient civilization, how chemistry was involved in, it was discussed in 2-3 pages. I'm not going to discuss in detail into those topics because it is only for the knowledge purpose. If you are interested, you can go through. Exam point of view, I don't find any that much of contribution from those topics, but still it will be useful for you to understand the cultural and ancient knowledge which we had in the older days. All these are talking about that, and is dealing with a different part of life, how chemistry was involved in. It is explained there in those pages. You can find that our ancient text, the contribution from our ancient text, it is also explained in the initial pages of the NCERT. Suppose if you find any of the competitive objective point of statements from the textbook, that you can simply highlight and go through. That's all. From the older textbook, many will be having older textbook with you, and that actually starting from importance of chemistry here. Sir, should we go through the importance of chemistry? I would say each and every line of NCERT is important, because we don't know exactly how a simple question is going to be presented taken between the lines of NCERT. For example, suppose if we go through this, if you concentrate on this area, hope you find the lines talking about cisplatin taxol, about drugs. Cisplatin, you may be aware of, it is used for cancer therapy. Cisplatin and taxol, and there is a talk on AZT, azithromycin, used for helping AIDS patients, like that. So such lines should be picked from NCERT to go through, because that can be a direct and simple question that you can expect. Okay, so even the introduction part you must go through line by line NCERT, and coming all the from there, it is starting from the nature of matter. You can go through the fundamentals of nature of matter. Actually, that is learned in the lower classes itself. Matter classified into physical classification, chemical classification. Physical classification, solid, liquid, gas. Chemical classification, hope you know, pure substances and mixtures. pure substances, elements, compounds like that, mixtures, homogeneous mixtures, heterogeneous mixtures, right? So that classification of matter, actually we are learning from the lower classes itself. Classification of matter, physical classification, chemical classification, pure substances, mixtures, homogeneous mixtures, heterogeneous mixtures. What is the difference between homogeneous and heterogeneous mixtures? Homogeneous mixtures means uniform composition. The mixtures having two or more substances mixed in a uniform composition is called a homogeneous mixtures, which will have a common unique phase. That is the point. While heterogeneous mixtures make a non-uniform composition and it will have a different heterogeneous phase in it. While elements, compounds, elements further classified into metals, non-metals, semi-metals, compounds classified into organic compounds, inorganic compounds. That variety of classification which actually you are learning in the lower classes, it is dealt here, which you can simply go through as a review, and the pattern of that classification is available in the NCERT. That is classification of matter. That is about the classification of matter. And there is a talk on atoms, molecules, what are atoms, what are molecules, how they act as a single entity, how it is different, right? Hydrogen atom, oxygen atom, hydrogen and oxygen combining, water molecule, like that. So such fundamental ideas are dealt there. Now coming to the properties of matter and their measurements. This is one area which I would like to talk about. Properties, various fundamental physical properties, derived physical properties, fundamental quantities, derived quantities, and various aspects related to that. This I would say, this you are dealing in detail in the physics first unit, units and dimensions. Units and dimensions, that is an area, the physics first chapter, which you can concentrate. And this is only preliminary fundamental ideas. What about you compared to what you learned there? The 7 fundamental physical quantities. The 7 fundamental physical quantities. These are the 7 fundamental physical quantities. All of you know: length, mass, time, electric current, thermodynamic temperature, amount of substance, which is the most important topic that we are going to discuss in the current chapter. Then luminous intensity, the 7 fundamental physical quantities, their symbol, their nature of SI unit and symbol of the unit. These things I'm sure you are learning in physics, and moreover in physics you are learning the derived quantities also, like density, specific volume, so many things you are learning. Derived quantities also you are learning in physics. So fundamental 7 fundamental physical properties and derived properties. That is a bit of introduction given in the chapter chemistry, which you can go through like this. And the definitions of SI system definition is also commented. For the knowledge purpose, you can go through this also. And see, this is an important area. This is an important one. Table 1.2, prefixes 1.3, prefixes used in SI system. I think many of you know regarding various higher prefixes and lower prefixes, like 10, deca, 10 raised to 2, hecto, 10 raised to 3, kilo, 10 raised to 6, mega. Many values already not. Like, I don't believe anybody who don't know what is kilo. I'm sure there is nobody who don't know what is milli, centi, etc. But there are some prefixes which you don't know, and straight away that can come for competitive exams as a direct question. Like octo, septo, fer. You see that femto, 10 power minus 15 called a femto. Pico, 10 power minus 12, commonly used unit. 10 power minus 12, pico, nano, that is non-thick. So many going to higher values also, mega, giga, tera, peta. So go through the prefixes, because that may be either used in some of the problems converting the units, or it can be a direct question also. You can expect a direct, whatever given in the textbook, you can expect as a direct question. Okay. So that is the thing. Then the units, the mass and the weight, volume conversions like this. Very simple, but so many make mistake doing calculations. You see, 1 liter, 1000 milliliter, that is 1000 centimeter cube, that is 1 decimeter cube. So those conversions, volume conversions, density, unit density, derived quantity, temperature. Temperature is an important area I would like to talk to you about. Temperature. Temperature, 3 units of temperature you must be thorough with. Kelvin scale, Celsius scale, Fahrenheit scale. Kelvin scale, Celsius scale, Fahrenheit scale. So this conversion you must be thorough. Right? This is calibrated with reference. You can see the freezing point of water, 0 degrees Celsius, 273.15 Kelvin. 273.15 Kelvin, 0 degrees Celsius, that is minus 32 degree Fahrenheit. For a better visualization, I will take this table. You see that table? The diagram, freezing point of water, 32 degree Fahrenheit, 0 degree Celsius, 273 Kelvin. And boiling point of water, 100 degrees Celsius, 373 Kelvin. Everybody know how to convert degrees Celsius to Kelvin, but many times we forget. Doing calculations, the temperature will be given in degrees Celsius. You simply forgot to convert into Kelvin scale and you make a mistake. That's quite naturally happening. So conversion is known to all. Human body temperature 37 degrees Celsius, 310 Kelvin, room temperature, and in degree Fahrenheit, 212 degree Fahrenheit. And the conversion between Celsius to Fahrenheit also very important. Conversion from Celsius to Fahrenheit is also very important. This formula, degree Fahrenheit is equal to 9 by 5 degrees Celsius plus 32. Degree Fahrenheit equal to 9 by 5 degrees Celsius plus 32. Right? So such conversions, the 3 important units of temperature, degree Celsius, Fahrenheit and Kelvin scale. So temperature unit conversion, you have to have a thorough look at, and you have to practice doing problems also. For example, you can expect some simple question. You try to find out the answer. At what value of temperature the degree Fahrenheit and degree Celsius coming same value? There can be some tricky questions like that. You try to find out. At what temperature point the value for degree Fahrenheit and degree Celsius? I think many of you know that answer. If you don't know, work out and find out. You can use the formula. Without using, you must be knowing many times. I think so. The temperature at which the value of degree Celsius and Fahrenheit coming same. Try to figure out. So such things to be taken care of in the units part. And then uncertainty in measurement. The topic uncertainty in measurement, precision, accuracy, right? Precision, accuracy, etc. regarding the measurements. That things again you are learning scientific notation, significant digits. These are the topics I am sure you might have heard about in physics and detailed dealt in physics. So after learning that topic, units and dimensions in physics, you can review this area and try practicing few problems given in the textbook and in the materials and all. Scientific, representing scientific notation, multiplication, division, addition, subtraction, significant figures, rules concerned to significant figures. 1, 2, 3, 4, 5. 5 rules are explained regarding significant figures. I am not going to the details of that because more than this you are learning in physics. After learning that, you can review this topic. Okay. See, the chemistry discussion basically starts from the laws of chemical combination. Chemistry discussion starts from the laws of chemical combination. Okay. So let's start our discussion in chemistry part. Laws of chemical combination. Laws of chemical combination. First one, law of conservation of mass. Law of conservation of mass, the fundamental law of chemistry known to all, proposed by the so-called father of modern chemistry, Antoine Lavoisier. Matter can neither be created nor be destroyed, but can be transferred from one form to another. This is The law of conservation of mass, right? Matter can neither be created nor be destroyed, but can be transformed from one form to another. And what is the basic application of this law? I think all of you know. Balancing of chemical equation is done based on this law. Hydrogen react with oxygen, you get water. But we are not happy with this formula. Am I right? Why? Because this is not explaining law of conservation of mass. The fundamental law is not explained here. Why? Because 2 hydrogen, H2 plus O2 giving H2, it is not a balanced equation. What is a balanced equation? 2H2 plus O2 giving 2H2O. Now only the equation is balanced. The mass available on the left hand side, the reactant side, should be equal to that in the product side. Law of conservation of mass. Once again, you have to think whether it is true always. Is it universally true? There are so many reactions, particularly nuclear type reactions where there is a mass defect. A certain small amount of matter is converted to energy. We can't say law of conservation of mass is hold good. So almost all chemical reactions we can say, in chemical reactions we can say balancing of chemical equation done based on the fundamental law of chemistry, law of conservation of mass proposed by Lavoisier, number 1. Number 2, it is law of constant proportion. Law of constant proportion. It is also called the law of definite proportion. Law of constant proportion, law of definite proportion, law of fixed proportion, proposed by Joseph Proust. It just states that a chemical compound always contains same elements combined in the same fixed proportion by weight. I repeat, a chemical compound, irrespective of the method of preparation, irrespective of the source of occurrence, always contains same elements combined in the same fixed proportion by mass. That is law of constant proportion. If you take NaCl, whether you get it from seawater, whether you get it from salt rock, whether you get it in the laboratory, it always contains sodium and chlorine in the ratio 23 mass of sodium versus 35.5 mass of chlorine. That is fixed. This is law of constant proportion. Once again, is it true universally? Not always. There are situations when this law is not hold good. For example, Fe 0.96 oxygen 1. Hope you know. Non-stoichiometric compounds. There are a lot of non-stoichiometric compounds, particularly given by transition, inner transition elements. Non-stoichiometric compounds may not be holding this idea good. Molecules involving isotopes may not be holding this idea good. Anyway, this is one of the most important fundamental law of chemistry. Law number 1, law of conservation of mass. Law number 2, law of definite proportion, law of fixed proportion, law of constant proportion. Law number 3. Third. What is the third one? Law of multiple proportion. Law of multiple proportion. Proposed by John Dalton. Law of multiple proportion, which states that when 2 elements combine to give more than one compound, when 2 elements combine, sulfur with the oxygen, to give more than one compound, sulfur dioxide and sulfur trioxide. When 2 elements combine to give more than one compound, when 2 elements combine to give more than one compound, the different masses of one of the elements that combines with the fixed mass of the other will be in a simple ratio. Here the mass of oxygen 32, here the mass of sulfur 32. Atomic mass of sulfur 32, oxygen 16 into 2, 32. And here atomic mass of sulfur 32, oxygen 16 into 3, 48. You see that the different masses of one of the element that combines with the fixed mass of the other will be in a simple ratio. So this ratio when you take, 32 is to 48. You can easily understand 2 is to 3 ratio. That is evident from the formula itself. That is evident from the formula itself. 2 oxygen here, 1 sulfur, 3 oxygen here, 1 sulfur. So it is 2 is to 3 ratio. This is what called the law of multiple proportion. When two elements combine to give more than one compound, the different masses of one of the elements that combines with the fixed mass of the other element remain a simple multiple figures, simple multiple ratio. Law of multiple proportion. He proposed this for mainly oxides, but it is applicable to all compounds. Okay. You can try working out yourself. You can try working out yourself the various oxides of nitrogen. Nitrogen combines with oxygen. You get different oxides. You get N2O, you get NO, you get NO2, you get N2O3, you get N2O5. The important 5 oxides of nitrogen. You can try work out. You can try yourself how the law of multiple proportion may be illustrated here. You might have worked out. I am just reminding you. After all, this is a rapid revision class. I am just reminding you the topics which already fed into your mind. I am reminding you. It's a reminding session basically. Okay, children? Yes. So law number 1, 2, 3. Next is one law which is not in the NCERT, but I would like to highlight here. That is law of reciprocal proportion. Law of reciprocal proportion. Law of reciprocal proportion proposed by J.B. Richter, which states that when you take three elements, say A, B, and C, imagine A and B combines in the ratio X is to Y by mass. Imagine A and C combine in the ratio X is to Z by mass. A combines with B, three different elements. A combines with B in the ratio X is to Y. A combines with C in the ratio X is to Z. And if B combines with C, they do so in the ratio either Y is to Z or a simple multiple of these values. A, Y is to B, Z. A and B can be same or different. So, AB combines in the ratio X by mass ratio. A separately combines with the C, XZ. Then B and C will combine in the ratio either YZ or a simple multiple. For example, carbon, hydrogen, oxygen. Carbon combines with the hydrogen, you get a methane in the ratio 12 is to 4. Carbon combines with oxygen, you can take carbon dioxide or carbon monoxide, I don't mind. It is 12 is to 32. Now you see, carbon mass is fixed. Hydrogen here is 4, oxygen here 32, and now when they combine, their mass ratio will be either 4 versus 32 or the multiple of this 4 and 32. You see, it is H hydrogen and oxygen. Imagine you take water, it is 2 is to 16, that is 4 is to 32. 2 is to 16, hydrogen 2, oxygen 60. It comes as a multiple of these figures. Hope you understand. So whenever three elements combine in such a way that AB combination XY ratio, AC combination XZ ratio, then BC combination will be either YZ ratio or a simple multiple. This is law of reciprocal proportion, also called a law of equivalent proportion. The idea of equivalent weight is derived from this law. Okay, so conservation of mass, constant proportion, multiple proportion, reciprocal proportion. Next one, Gay-Lussac's law. Next one, Gay-Lussac's law of gaseous volumes. Gay-Lussac's law of gaseous volumes. That is the next one. This is applicable to gaseous materials, not for solids, not for liquids. So any reaction where there is a solid, You don't apply for solids. If there is a liquid, don't apply for liquids. It's applicable only for gases. Okay, Gay-Lussac's law of gaseous volume. Okay, what is the law commenting about? When there is a gaseous reaction involving gaseous reactants and products, it says that there exists a simple ratio between the volumes of reactants and products. For example, if you take 2SO2, which is a gas, react with O2, which is a gas, giving 2SO3. This is the balanced equation. All of you easily understand. 2 mole SO2 react with 1 mole O2, you get 2 mole SO3 at a particular temperature. Okay, so there is a mole ratio 2:1:2, and same will be the volume ratio. All of you understand, at a constant temperature and pressure, number of moles is directly proportional to volume, is directly proportional to number of moles. So mole ratio will be same as volume ratio. So what you can understand is 2 liter SO2 will react with 1 liter O2 and you will get 2 liter SO3 at a particular fixed temperature. This is what called the Gay-Lussac's law of gaseous volumes. There exists a simple ratio 2:1:2. There exists a simple ratio between volumes of reactants and products, gaseous reactants and products in a particular gaseous reaction. This is Gay-Lussac's law of gaseous volumes. We are going through the fundamental laws of chemistry. There is one more we need to discuss. So which are laws? Law of conservation of mass, definite proportion, multiple proportion, reciprocal proportion, Gay-Lussac's law. Now, one more left, Avogadro's law. Avogadro's law. Avogadro's law, known to all, equal volume of all gases under the same condition of temperature and pressure contains equal number of moles, equal number of molecules. I repeat, equal volume of all gases under the same condition of temperature and pressure. Imagine you are taking 10 liters of hydrogen gas at a particular pressure. You are taking 10 liters of oxygen gas at the same pressure temperature. You are taking 10 liters of nitrogen gas at the same pressure and temperature. So 10 liter hydrogen, 10 liter oxygen, 10 liter nitrogen at the same condition of temperature and pressure. At the same condition of temperature and pressure. Equal volume of all gases. I am taking another gas X. I am taking another gas X. Equal volume of all gases under the same condition of temperature and pressure contains equal number of molecules, equal number of moles. Here the number of moles equal to X, then here also will be X, here it will be X, here it will be X. Suppose the number of molecules here is capital N, here also number of molecules is same capital N, here is number of molecules same capital N, here also same N. So equal volume, equal volumes of all gases under the same condition of temperature and pressure contains equal number of moles, equal number of molecules. That is Avogadro's law, known to all. These are all the fundamental laws of chemistry which is important from the starting segment of this chapter. What are the fundamental laws? Law of conservation of mass, law of definite proportion, law of multiple proportion, law of reciprocal proportion. I said not in the text, but it's better to know that competitively. Then Gay-Lussac's law of gaseous volumes, and now Avogadro's law. Is it clear? Is it clear? Right. So these areas are dealt in the NCERT segment, which you can find law of conservation of mass, definite proportion, multiple proportion, Gay-Lussac's law, Avogadro's law, all are explained here. Dalton's atomic theory, you can go through Dalton's atomic theory. A few points are commented here. Old theory. Matter consists of individual atoms. All atoms are identical in properties. Atoms of different elements are different in mass. Compounds are formed when atoms combine in a fixed ratio. Chemical reaction involve reorganization of atoms. These are neither created nor destroyed, etc. These are things which are from the Dalton's atomic theory. Then it is atomic mass, molecular mass. Atomic mass, molecular mass. All of you know how to find the atomic mass and what is the relative atomic unit. What is the relative atomic unit? It is AMU, unified mass. Unified mass. What is a unified mass? What is unified mass? Relative atomic mass unit. AMU. We call it as unified mass. Unified mass. That is represented as U. This is nothing but 1/12th mass of carbon 12 isotope. This is one unified mass. One unified mass means 1/12th mass of carbon 12 isotope. According to the latest accepted standards. Older days it was hydrogen as one unified mass. Then it was oxygen standard reference. Now the latest references we have according to SI systems. One unified mass is 1/12th mass of carbon 12 atom. Right? Suppose we take water molecule. Suppose we take water molecule and we say 18 unified mass. That means we try to convey a message. What is the message? Water molecule is 18 times heavier than one unified mass. What is one unified mass? 1/12th part of carbon 12 atom. 1/12th part of carbon 12 atom, that is one unified mass. And water molecule is 18 times heavier than one unified mass. That is for the knowledge which you must know regarding atomic mass, molar mass. But usually we take relative atomic mass, average atomic mass. How to take the average atomic mass? What is the idea of taking average atomic mass? Suppose you have an element X, atomic mass 20, which is available 30%. And you have same X 21, which is available, say, 60%. And another isotope X with a 22, which is how much? 10%. Imagine an element X, which are isotopes. What is meant by isotopes? Same atomic number, different mass number. That is called isotopes. Okay. X, 3 isotopes are available. Having mass number 20, the relative abundance is 30%. Having mass number 21, the relative abundance is 60%. Having mass number 22, the relative abundance is 10%. Just imagine. Okay. How to find the average atomic mass? All of you know what is the way to find the average atomic mass? Average atomic mass. How to find? It is 30 into 20 plus 60 into 21 plus 10 into 22 divided by 100. I don't have to tell you the importance of having mathematical numerical skill. The importance of numerical skill and the various mathematical tricks involved in calculation, which is how much important in competitive exams. I don't have to tell you, it's very, very important. And you are going to witness various kind of that tips and tricks when you come to the class. When you attend to the class over here, when you go to attend the course of study, in the class you can find various tips and tricks we are going to introduce regarding how to improve the numerical skill. See, many children are having a problem of numerical skill, numerical calculation problem. We are going to provide various techniques for that. So, such a calculation, many people, the numerical calculation is very simple. For majority, that's a problem. I know that. Right? So, once you look at a question and data, there are so many easy ways how to crack it easily from the given 4 choices. So anyway, traditionally, this is the way to find the average atomic mass, the percentage into mass, the percentage into mass, the percentage into mass, they divided by total 100. That will give you average atomic mass. Okay. So regarding AMU scale, unified mass, average atomic mass, molar mass, formula mass, where we take formula mass, I don't think, yeah, some of you might have heard about formula mass means for mainly ionic compounds. For ionic compounds, we can't say molecular mass, molar mass, it is formula mass. For example, NaCl. NaCl molar mass is 58.5, 23 plus 35.5, 58.5. But that is not a molecular mass because there is no molecule. It is only formula. NaCl is a formula and is called a formula mass. Okay. Then a very, very important area from the chapter, mole concept. Mole concept. Calculation related to mole concept. Right? All of you know what is meant by the fundamental unit mole. What is fundamental unit mole? Mole designated by N. What is mole? Mole means any material that contain Avogadro number of entities. That is 1 mole. 1 mole atom means the substance containing Avogadro number of atoms. 1 mole molecules. Avogadro number of molecules. 1 mole ions. 1 mole electrons. 1 mole protons. 1 mole of any material. It contains Avogadro number of entities. 1 mole means Avogadro number of entities. That is 1 mole. Avogadro number, all of you know, 6.02 into 10 power 23 entities. Entities means atoms, molecules, ions, electrons, protons, anything. Sir, why you are talking about atoms, molecules, electrons, ions? Is it because chemistry? No, I can talk about Avogadro number of mangoes. I can talk about Avogadro number of eggs. I can talk about Avogadro number of anything. But it's not going to work out because we never can think about Avogadro number of mangoes. How will you handle it? Avogadro number of eggs. How you are going to handle it? How you are going to handle it? We can't think about Avogadro number of matter for macroscopic objects. I remember seeing one numerical problem which is quite interesting. The problem is coming, you can try. The problem is like this. The problem is quite hypothetical. You see, the problem is coming like this. How much time it will take? How much time it will take to spend Avogadro number of rupees if you are spending 1 crore rupees per second? I'll repeat. Imagine you are rich enough to have Avogadro number of rupees with you. And imagine you are spending 1 crore per second. In 1 second, you are spending 1 crore. Purely hypothetical. The question is, how much time it will take to spend Avogadro number of rupees? You can try yourself. How much seconds? How much minute? How much hours? How many days? How many weeks? How many months? How many years? You can try. You can try yourself and you are going to get amazing data. And that tells you why this mole concept is not applicable to macroscopic objects. It is applicable to microscopic objects, atoms, molecules, ions, electron, proton, neutron, etc. No problem. You can talk about 1 mole water, no issue. You can talk about 1 mole water. What is 1 mole water? It is molar mass in grams. That is 18 gram water. What is 18 gram water? Density of water is 1 gram per ml. 18 gram means 18 ml. 18 gram means 18 ml. You can easily take 18 ml of water in a small vessel. That is 1 mole water. And that contains Avogadro number of water molecules. That is mole concept. It gives us an idea regarding a definite mass of material versus number of particles in that. That is mole concept. If you take a definite mass of material, if you take a definite mass of water, how many molecules are there? How many atoms are there? How many electrons are there? How many hydrogen atoms are there? How many oxygen atoms are there? How many protons are there? Everything you can calculate. That is the context of mole concept idea. Right? Learning with the mole concept idea, you need to have three important formulae finding number of moles. Number of moles is equal to mass in grams. Mass in grams. Divided by molar mass. All of you know number of moles is equal to mass in grams by molar mass. You can apply for any material. Number one. Number two, applicable only for gases. Number of moles is equal to volume of gas. Volume of gas at STP divided by molar volume. What is molar volume? 22.4 liters according to old standards and 22.7 liters according to new standards. This is old standard and this is new standards. Remember, this is applicable only to gases. This is applicable to all matter. This is applicable only to gases. Number of moles is equal to volume of gas at STP divided by molar volume. What is molar volume? 22.4 liters. If you take volume here in liter, you take volume here in liters. If you take volume here in milliliter, you take milliliters. 22,400 milliliter at STP. According to old STP standards, pressure 180 atm. It is 22.4 liter. According to new STP standards, pressure 1 bar. 1 bar is 0.98 atm. Slightly lower pressure. So the volume is slightly higher, 22.7. Still, for calculation purpose, many problems we take older data. That's why I have given both the data. So for any matter, when mass is given, mass by molar mass, number of moles is equal to mass by molar mass. Number of moles is equal to volume by 22.4 or 22.7. Remember, only at STP, only for gases. And number three, number of moles is equal to number of particles divided by Avogadro number. Number of moles is equal to number of particles by Avogadro number. You can remember these three important formulae related to number of moles. Number of moles is equal to, for any matter, whether solid, liquid, gas, mass by molar mass. For any matter, whether solid, liquid or gas, number of particles by Avogadro number. Only for gases at STP. Only for gases at STP. Only for gases at STP. When volume given, number of moles is equal to volume by molar volume. What is molar volume? Volume of 1 mole of any gas at STP. It is fixed 22.4 liters old standard, 22.7 liters new standard. Okay. Working out based on these formula, we call it as mole concept. Suppose I tell you how the problems may encounter. Suppose it is given 1 kilogram of sugar. 1 kilogram of sugar. How do you find the number of moles? Number of moles is equal to sugar, you know, C12H22O11. Okay. How many moles are there? Number of moles is equal to mass in gram, 1000 divided by molar mass. You need to know molar mass of many popular molecules. You must know. Okay. It is 342. You can find the number of moles. Okay. So how many molecules are there? How many molecules are there? 1 mole contains Avogadro number of molecules. So number of molecules is equal to number of moles into Avogadro number. So you can take 1000 divided by 342 into 6.023 into 10 power 23. This is the number of molecules. So this is number of moles and this is number of molecules. They may ask you how many carbon atoms are there. How many carbon atoms are there? Number of carbon atoms. Number of carbon atoms. How many? It is number of moles into Avogadro number into number of carbon atom per molecule into 12. So how do you do? It is 1000 by 342 into 6.02 into 10 power 23 into 12. So this is number of moles. This is number of molecules into 12 number of carbon atoms into 22 number of hydrogen atom into 11 number of oxygen atom, right? And 12 plus 22, 32, 34, 44, 45. There are total 45 atoms. They may ask you how many total atoms. How many total atoms? How many total atoms? It will be number of, you see, number of moles into Avogadro number. This is the number of molecules into 45. That is the number of total atoms. So various calculations like this related to number of moles, number of molecules, number of atoms, number of carbon atom, number of hydrogen atom, number of oxygen atom, number of proton, number of electron, number of neutron. Many problems may be encountered based on the mole concept idea. Okay, so that is an important area from the chapter, mole concept and related things. Then there is percentage composition. That's an important area. Percentage composition. How do you find the percentage composition? All of you know. Suppose they ask you what is the percentage? What is the percentage of carbon in acetic acid? What is the percentage of carbon in acetic acid, CS3COOH? What is the percentage of carbon? How to calculate? Percentage of carbon equal to mass of carbon divided by molar mass into 100. What is mass of carbon? There are 2 carbon atoms. So it will be 24. 12 into 2, 24 divided by molar mass of acetic acid. I told you, molar mass of commonly encountered molecules. It should be there in your tip. Okay, it is 60 into 100. You easily work out 40%. Percentage composition. How do you find the percentage of an element in a compound? It is the weight of that element divided by the total molar mass into 100. What is the percentage of nitrogen in urea? What is the percentage of nitrogen in urea? You must know the formula of urea first. You must know the formula of urea first. What is the formula of urea? It is NH2CONH2. So what is the percentage of nitrogen? Percentage of nitrogen, there are 2 nitrogen. So it is 2 into 14, 28 divided by the total molar mass. It is 60 into 100. Is it molar mass of both the same? Yeah, it should be 2 nitrogen, 4 hydrogen, carbon, oxygen. Yeah, it is 60 here and 60 there. This is percentage of nitrogen. This is molar mass of acetic acid. Accidentally, molar mass of the 2 compounds came same here. Please don't misunderstand. This is molar mass of acetic acid and this is molar mass of urea. Both came accidentally same. Okay. So that way you can find a percentage. Percentage composition. All of you know how to find a percentage. An important point is how do you find the empirical formula and molecular formula. That is an important area from the chapter. Empirical formula and molecular formula. Empirical formula and molecular formula. First of all, what is empirical formula? Empirical formula is the simplest formula that represents relative number of atoms present in a compound. Empirical formula is the simplest formula that is present in that is representing the relative number of atoms present in a molecule. That is empirical formula. What is molecular formula? Molecular formula is actual formula. We can refer what is empirical formula, molecular formula with reference to a problem. Suppose you are given with a question. carbon there, hydrogen there, and oxygen there. Carbon given as 40%, hydrogen given as some 6.6%, and oxygen given say 53.4%. That means the remaining. Overall 100%. So carbon 40%, hydrogen 6.6%, oxygen 53.4%. Suppose you find such a numerical. This is a question coming in front of you and ask you to find out the empirical formula. How do you find the empirical formula? Very simple. Step 1. It is the mass, the percentage divided by the atomic mass. So 40 divided by atomic mass of carbon, 12. You get some 3.3 something. Now percentage is 6.6 divided by atomic mass of hydrogen. You get 6.6. Here percentage 53.4 divided by atomic mass of oxygen. That is also somewhat 3.3. You find out the relative number of atoms like this. The given percentage divided by atomic mass. 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 You get a figure. Make it into a whole number ratio. How to make the whole number? Very simple. Very simple. It is 3.3, 6.6, 3.3. It is 1, 2, 1. So the empirical formula will be CH2O. This is the empirical formula. This is the empirical formula. How to get the molecular formula? How to get the molecular formula? Molecular formula is equal to empirical formula taken n times. What is n? What is n? N is equal to molar mass divided by empirical formula mass. Molar mass will be given in the question. Molar mass can be determined experimentally. There are several experiments for finding the molar mass. Imagine the molar mass is determined experimentally. That data will be given to you. Say for in this question, imagine the molar mass is given 60. You can find the n value. How to find the n value? N equal to, imagine molar mass in this question given as 60. It is 60 divided by empirical formula mass. What is empirical formula mass? Carbon 12, hydrogen 2, oxygen 16. How much? It is, yes, 30, isn't it? 16, 20, 30. So it is 60 by 30. You are getting n equal to 2. You can find the molecular formula. It is molecular formula, is empirical formula taken n times. So it will be CH2O twice. That is C2H4O2. C2H4O2. It could be the previous molecule we were talking about. CH3COOH. C2H4O2. C2H4O2. Acetic acid. So what all things we did? The percentage was given. Divided by atomic mass, we get the relative number of atoms. Make it into whole number figure. You get empirical formula. And molar mass will be given in the question. So molar mass by empirical formula mass, you get n. Empirical formula taken n times, n equal to 2. Empirical formula taken n times, you get a molecular formula. Right? Different molecules can have the same empirical formula. Different molecules can have the same empirical formula. You see this? Empirical formula for acetic acid. You see, CH2O. This, if you take 2 times, it is acetic acid. This, imagine you take 6 times. That is C6H12O6. That is glucose or fructose. So this is empirical formula. What is empirical formula? The simplest formula representing the relative number of atoms present in a compound. What is molecular formula? Molecular formula is actual formula. The empirical formula taken 2 times, you get acetic acid. This formula taken 6 times, you get glucose, fructose. The empirical formula taken n times, you get molecular formula. I hope you understood. So how to find the empirical formula? How to find the molecular formula? What are the calculations concerned? Please go through. Right? So that is an important area from the topic. Then it is about stoichiometric calculations. Stoichiometric calculation. Stoichiometric calculation is the most important delta area in the chapter. Not in the theoretical aspect, but in a problems area. Doing numericals. Doing numericals, it is very, very important. For example, if you encounter a question, how many moles oxygen is produced by the complete decomposition of, say 5 moles of potassium chlorate. Imagine a question, 5 moles of potassium chlorate undergo decomposition. How many moles of oxygen is evolved? You must know the stoichiometry. That's why it is called stoichiometric calculation. KClO3 upon decomposition, you get KCl and O2. 2 KClO3 giving 2 KCl plus 3 O2. Isn't it balanced? Isn't it balanced? This is the balanced stoichiometry. So you must know the balanced stoichiometry for doing stoichiometric calculation. And this calculation may be involving number of moles, may be involving mass, may be involving volume for gases. It can be. Okay. So let's see. What was my question? 5 mole potassium chlorate decomposes. How many moles oxygen was obtained? 5 moles potassium chlorate decomposes. How many moles oxygen was obtained? Very simple, no? 2 mole. 2 mole potassium chlorate gives you 2 mole KCl and 3 mole oxygen. So 2 mole potassium chlorate gives you 3 mole oxygen. Therefore, 1 mole potassium chlorate, you get 3/2 mole oxygen. Therefore, 5 mole potassium chlorate, you get 3/2 into 5. That is 15/2 mole of oxygen. 7.5 mole oxygen is obtained. The question may be in terms of volume. They may ask you how much volume of oxygen obtained at STP. You know 1 mole. You know 1 mole of any gas. It is 22.4 liter at STP. Therefore, 7.5 mole. How much? It is 22.4 into 7.5 liters at STP. Clear, right? Clear. So the question can be based on mass, based on number of moles, based on volume. This is stoichiometric calculation, which need to be many problems need to be practiced, and that is what the one which we are going to do in the classes, doing problems, practicing, expertising ourselves, doing numerical stoichiometric calculations. Okay. A very important point comes is regarding limiting reactant, a topic called limiting reactant. Limiting reactant. For example, suppose we take the stoichiometry N2 plus 3H2 giving 2 ammonia. Imagine it is given to you in a problem 10 mole each of nitrogen hydrogen taken. 10 mole each of nitrogen hydrogen taken to produce ammonia. They ask you what is the limiting reactant, which is the limiting reactant, and what is the quantity of ammonia formed. This is an important question from the important context from the area. Identifying limiting reactant. I'm sure you might have heard about limiting reactant is the one which is completely consumed. A reactant which is completely consumed. That is called a limiting reactant. For in this question, for example, a numerical question given to you, 10 mole each of nitrogen hydrogen taken. Which is the limiting reactant? And what is the amount of product formed? You see, 1 mole nitrogen react with 3 mole hydrogen and you get 2 mole ammonia. So here you can understand. How do you understand? 1 mole require 3 mole. The amount of hydrogen required is 3 times. Amount of hydrogen required is 3 times. Here we are taking 10 mole. So here it should be 30 mole. But what given is only 10 mole. You see, 1 mole requires 3 times, 3 mole. Therefore, 10 mole requires 30 mole. So hydrogen required is 30 mole, but given is only 10 mole. That means hydrogen is the limiting reactant. Hydrogen is the limiting reactant in this case. Or you think reverse. 3 requires 1. 3 requires 1. Therefore, 10 requires how much? 1 requires 1 by 3. 1 mole requires 1 by 3. Therefore, 10 mole. This given is 10 mole. Hydrogen given is 10 mole. 10 mole requires 10 by 3. That is 3.33 mole is required. But given is excess. The amount of hydrogen required, nitrogen required is only 10 by 3. 3.33 mole. But given is 10 mole. That means 6.7 moles excess. So this is excess reactant. And this is limiting reactant. And this will decide the amount of product formed. Amount of product formed is decided by the amount of limiting reactant. Now we can think about 3 mole hydrogen will give you 2 mole ammonia. 3 mole, this is the limiting reactant. 3 mole hydrogen will give you 2 mole ammonia. 1 mole will give you 3, you will get 2 mole. Therefore, 1 mole will give you 2 by 3 mole. Therefore, 10 mole will give you 2 by 3 into 10. That is 20 by 3. You get how much? 6.66 mole ammonia is formed. This kind of questions, identifying limiting reactant, identifying the product, identifying the excess reactant, how much it is excess, who is the limiting reactant, naturally who is the excess reactant, then how much it is excess, what is the amount of product formed. This is one important area from the stoichiometric calculations, and this is not to be dealt like a theory, it is more to be practiced. Is it clear? Right. So that probably one of the most important area from the chapter, or the core content of the chapter, I would say. Core content of the chapter. While the last part of the chapter, that is concentration terms. The last part of the chapter, that is reactions involving in solution. Various concentration terms. That is also very important. Various concentration terms. Various concentration terms. Number 1, mass percentage. Number 1, mass percentage. What is mass percentage? Mass of solute in 100 mass of solution. What is mass percentage? Mass of solute by mass of solution into 100. That is mass percentage. Simple idea. Number 2, volume percentage. Volume percentage. What is that? Quite similar. Volume of solute by volume of solution into 100. Volume percentage. Mass percentage, volume percentage, different concentration terms. Different concentration terms. Because we deal with a different kind of solutions. So mass percentage, volume percentage. Third one, mass volume percentage. Very important. Mass volume percentage. That is mass of solute in 100 ml of solution. Mass of solute in 100 ml of solution. So that will be mass of solute by volume of solution into 100. So mass percentage, volume percentage, mass volume percentage. Okay. Then, not over, not over. Very important one. Molarity. Molarity. Capital M. Molarity. What is molarity? Molarity. Very popular concentration term. Molarity. It is the number of moles of solute per liter of the solution. Molarity is mole per liter. Number of moles of solute. Number of moles of solute by volume of solution in liters. The unit of molarity is mole per liter. Mole per liter. So molarity M equal to N by V. Or for calculations, many times we make use of number of moles is equal to molarity into volume in liter. You might have seen. Number of moles is equal to molarity into volume in liter. Same. Molarity is equal to mole per liter. Or you can make use molarity is equal to mass of solute divided by molar mass of solute into 1000 divided by volume of solution in milliliters. Right? So these kind of concentration terms and its numerical application we are going to discuss in the classes with a whole lot of numericals in different varieties. Okay. And regarding molarity, when you learn, you must know molarity dilution equation. Dilution equation. What is dilution equation? Imagine one solution given to you and you are diluting. Imagine a solution given to you and you are diluting. You have a solution, molarity M1, volume V1. You are adding water. You are adding solvent. Dilution means adding solvent. The concentration changes to M2, volume changes to V2. Then what is the formula? M1 V1 equal to M2 V2. Before and after dilution, the number of moles remain constant. N is equal to M into V. The number of moles of solute will remain same before and after dilution. So what is the formula? M1 V1 equal to M2 V2. What is M1 V1? Before dilution. What is M2 V2? After dilution. This is called a dilution equation. And now another kind of equation. Suppose you have HCl solution 1 having molarity M1 volume V1. HCl solution 2 having molarity M2 volume V2. What is, you are going to mix this. What is the molarity of resultant mixture? M3 is equal to M1 V1 plus M2 V2 divided by V1 plus V2. Rather, I would say V final. Sometimes they may give a different volume, final volume. So, 2 HCl solution, molarity M1 volume V1, molarity M2 volume V2. You are mixing the two solution. What is the resultant concentration? Resultant concentration N3 is equal to M1 V1 plus M2 V2 by V1 plus V2 or V final. Right? That is molarity. So mass percentage, volume percentage, mass volume percentage, molarity. Then it is normality. Normality. Normality means capital N. Normality means number of gram equivalents. Number of gram equivalents of solute per liter of solution. Number of gram equivalents of solute per liter of the solution. It is N equal to equivalents per liter, or number of equivalents, is equal to, capital N. Number of equivalents is equal to normality into volume in liter. Normality related problems we don't expect much, but simply for the purpose of competitive purpose I am just telling you. Okay, number of equivalents is equal to normality into volume in liter. How does this normality comes out to be? Normality N is equal to mass of solute into 1000 by equivalent mass of solute into volume of solution in milliliters. It is quite similar to molarity formula. Molarity is equal to mass of solute into 1000 divided by molar mass of solute into volume of solution in milliliter. Here it is equivalent mass, here it is molar mass. How are they related? How is the equivalent mass and molar mass are related? Many of you know equivalent mass is equal to molar mass by n factor. What is n factor? Equivalent mass is equal to molar mass by n factor. Molarity is mass of solute into 1000 by molar mass into volume in milliliters. What is normality? Mass of solute into 1000 by equivalent mass into volume in milliliters. All are same. Where is the difference? Where we have the difference? The difference is encountering in this one. Here molar mass, but there equivalent mass. What is equivalent mass? Equivalent mass of a material is equal to molar mass divided by n factor. What is n factor? For elements, n factor is valency. Sodium monovalent, potassium monovalent, calcium divalent, n factor is 2. Aluminium trivalent, n factor is 3. So for elements, n factor is valency. For compounds, n factor is the charge of the total charge of either cationic part or anionic part. For example, if you are taking Al2O3, the charge of aluminium is 3 plus and the cationic part is 3 into 2, 6. That is n factor. Or you can take anionic part, 2 minus into 3. That is again 6. So the total charge of either cationic part or anionic part, that is called the n factor for compounds. For elements, n factor is valency. For compounds, n factor is total cationic or anionic charge. For acids, n factor is basicity. For hydrochloric acid, basicity is 1. For sulfuric acid, basicity is 2. Okay. For phosphoric acid, H3PO4, n factor is 3. Like that. So that you can make use for finding the relation between molarity and normality. For example, if you take a hydrochloric acid, imagine molarity is X, normality is same as X. No change because n factor is 1, molar mass and equivalent mass are same. Suppose you encounter sulfuric acid. Imagine you take sulfuric acid where n factor is 2. Imagine molarity is 0.1. Then normality will be 0.1 into 2. That is 0.2. So try to encounter those things. So mass percentage, volume percentage, mass volume percentage, molarity, normality. Next is molality. Molality designated by small m. What is molality? Number of moles of solute in 1 kilogram solvent. Number of moles of solute in 1 kilogram solvent. So number of moles of solute by weight of solvent in kilogram. That is molality. Small m. The unit is mole per kg. The unit is mole per kg. So how do you write? M equal to the detailed expression. The detailed expression molality M is equal to weight of solute into 1000 by molar mass of solute into weight of solvent in gram. This is molality. Okay. So mass percentage, volume percentage, mass volume percentage, molarity, normality, molality. Another important one is mole fraction. Mole fraction. Another concentration term. Mole fraction. Designated by chi or simply X. Imagine you have a mixture. Imagine you have a mixture of component A and B. Number of moles of A, Na. Number of moles of B, Nb. What is mole fraction of A? Mole fraction of A is equal to number of moles of A divided by N total. That is number of moles of A by number of moles of A plus number of moles of B. That is mole fraction. So what is mole fraction? Number of moles of one component out of total number of moles. And I am sure you understand any fractions when you take. There is no unit. Mole fraction has no unit. Sum of mole fractions is unity. Very important. Sum of mole fractions is unity. What is chi B? Chi B is equal to Nb by Na plus Nb. I don't have to tell you chi A plus chi B is equal to 1 or chi B equal to 1 minus chi A. These things are very, very, very important. And finally, a most commonly encountered unit, ppm. ppm. You might have seen many times using ppm. ppm. ppm means parts per million. Parts per million. What is that? ppm. ppm is equal to mass of solute by mass of solution into 10 raised to 6 million out of million. Percentage is out of 100. So what is per million? 10 raised to 6. So mass of solute by mass of solution into 10 raised to 6. Not necessarily mass by mass. It can be volume by volume. ppm can be mass by mass. ppm can be volume by volume. ppm can be mass by volume. ppm can be represented in different way. Mass by mass, volume by volume, mass by volume. The most famous unit of ppm is milligram per liter. 1 ppm equal to 1 milligram per liter. Milligram per decimeter cube. That is ppm. Or microgram per ml. That is ppm. So these concentration terms and the numerical parts concerned to that. That probably is vital area from the chapter. So two important area from the chapter as far as this chapter is uniquely encountered in all other chapters. The applications of this chapter concept is applied in all other chapters. That's why the chapter is called Some Basic Concepts of Chemistry. And what are the two important area? Number one, mole concept. Not two, I would say three. Number one, mole concept. Number two, stoichiometric calculation and the related workout. And number three, concentration terms applied in problems. That probably is the last portion of the chapter to discuss or having a revision or to review from the chapter. And herewith I am going to conclude. Before concluding the chapter, which we had in this very short span of time as a rapid revision, before concluding, let me tell you one by one which all points. We started from the historical aspects of introduction regarding ancients' contribution of our ancestors, 2-3 pages. Then it was classification of matter. Then it was various scientific notation, significant figure, precision, accuracy, etc. That I told you to concentrate on units and dimensions, physics chapter 1. Then we entered into chemistry, fundamental laws of chemistry. Law of conservation of mass, law of definite proportion, law of multiple proportion, reciprocal proportion, Gay-Lussac's law of gaseous volumes, Avogadro's law. Dalton's atomic theory. Atomic mass, molar mass, AMU, unified mass, related. Average atomic mass. How to find the average atomic mass? Right? Then what was it? Formula mass. Then percentage composition. Then mole concept. Number of moles, number of molecules, number of atoms, electrons, mole concept idea. Then percentage composition, I told you. Empirical formula, molecular formula. How to find empirical formula, molecular formula, relations, etc. Then stoichiometric calculations. Limiting reagent. What is limiting reagent and how it is applied? And finally, concentration term. Which all concentration terms? Mass percentage, volume percentage, mass volume percentage, molarity, normality, modality, ppm, mole fraction, etc. Right? These are the major important points you need to review and practice from the chapter Some Basic Concepts of Chemistry. Okay? With another chapter in rapid revisions, we will meet in another video. Okay? Till then, bye. See you. Take care. Study well.